This is a hands-on class, so open the lab guide and run pods alongside me. Last class you learned the object model and A20 tool, how everything in Kubernetes is a declared object with the spec that the cluster works to satisfy. Today, we meet the most fundamental object of them all, the one that everything else exists to manage, the pod. When people first come to Kubernetes, they expect the basic unit to be the container and A200. After all, you learn Docker, you build images, you run containers. But Kubernetes does not actually run containers directly. It runs pods. A pod is the smallest thing you can deploy in Kubernetes, a thin wrapper around one or more containers, and it is the atom from which the entire system is built. Deployments manage pods. Services route to pods. Scaling means more pods. So if you truly understand the pod and 8424, what it is, why it wraps a container, what its containers share, how it lives and dies, and 8424, then every higher level concept in Kubernetes suddenly has a solid foundation to stand on. Today, we open the pod right up. By the end, you will know exactly what a pod is, why it exists, and the crucial fact that pods are disposable and A200-202, which explains why the rest of Kubernetes is shaped the way it is. Let us dig in. Here is our path for today. First, what a pod actually is. Second, how a pod differs from a container. Third, multi-container pods. Fourth, what containers in a pod share an 821, network and storage. Fifth, the pod lifecycle. And sixth, the crucial fact that pods are ephemeral. Let us dive in. Let us start with the definition, because it reframes everything you thought you knew about running containers on Kubernetes. A pod is the smallest thing you can deploy in Kubernetes. It is a wrapper around one or more containers that are always kept together and A212, scheduled together onto the same node, started together and stopped together. When you ask Kubernetes to run your application, you are really asking it to run a pod, and the pod is what carries your container. It is the fundamental unit of deployment, the atom of the whole system. The point that surprises newcomers is this: Kubernetes never schedules or manages a bare container. It always works in terms of pods. You do not tell Kubernetes and ek sores ores tutuhing. Run this container and ek sores tutuhing. You tell it and ek sores tutuhing. Run this pod and ek sores tutuhing. And the pod contains the container. Every mechanism in Kubernetes and 812, scheduling onto nodes, health checking, scaling, networking, and 812 operates on pods as its unit. The container is still there, doing the actual work, but it is wrapped inside a pod that Kubernetes actually holds and manages. Why introduce this wrapper at all, rather than managing containers directly? Because Kubernetes needs to attach things to a running workload that a bare container does not have on its own, and 812, a stable identity, a network address, shared storage, a defined lifecycle, and the ability to group a few tightly coupled containers as one. The pod is the object that provides all of that. It is the unit Kubernetes can reason about, and everything else is built on top of it. Grasp that the pod is the true unit, and the mental model clicks. So the takeaway: a pod is the smallest deployable unit in Kubernetes and 824. A wrapper around one or more containers kept together, and 824. And Kubernetes always schedules and manages pods, never bare containers, because the pod provides the identity, networking, storage, and lifecycle a raw container lacks. Let us sharpen the distinction between a pod and a container, because holding these two ideas clearly apart prevents a lot of confusion. A container is what you already know from Docker: one packaged process, your application and its dependencies bundled into an image, running in isolation. It is a single, self-contained unit of software. The container is where your actual code executes, and 82112, the web server, the API, the worker. Nothing about Kubernetes changes what a container fundamentally is. A pod is a wrapper around that container that adds the things Kubernetes needs to manage it as part of a cluster. It gives the workload an identity within the cluster, a network presence, a place for shared storage, and a managed lifecycle. Where the container is a general concept from the container world, the pod is Kubernetes and icon for SETI 9, own unit and icon for SETI, the layer at which Kubernetes takes over and provides its orchestration. Think of the container as the engine and the pod as the car body around it that lets Kubernetes actually drive it. So the clean way to hold it, the container is what runs, the pod is the Kubernetes level unit that runs it. In the very common case, a pod contains exactly one container, and the two feel almost synonymous and A200, which is why beginners conflate them. But they are different layers with different jobs. The container packages and runs your process, and the pod is the managed Kubernetes object that wraps it, gives it a cluster identity, and is the thing every other Kubernetes feature acts upon. Keep that layering clear and the rest follows naturally. So the takeaway, a container is your packaged, running application process, while a pod is the Kubernetes level wrapper that adds cluster identity, networking, storage, and lifecycle around it, and AT112, the container, is what runs. And the pod is the managed unit Kubernetes runs it, as even though a single container pod makes them feel synonymous. We keep saying a pod holds an A2020, one or more an A2 or 21 containers. Let us look at that N82 sit or modern AT200 case, because it reveals why the pod concept exists at all. The overwhelmingly common situation is one container per pod N82.5, your single application, wrapped in its pod. For most workloads, that is exactly right, and you should default to it. But a pod can hold more than one container, and it is designed for a specific situation, when a few containers are so tightly coupled that they must run as a single unit on the same node, sharing the same fate. The classic example is the sidecar pattern. Your main container runs the application. A second smaller sidecar container runs alongside it doing a supporting job, and A2112, shipping the app in 89 sex logs to a central system, say, or acting as a local proxy, or refreshing some data the app reads. The sidecar is not a separate service. It exists purely to help the main container, and it only makes sense to run right next to it. Putting them in one pod expresses exactly that, and A2112. These belong together, and A2121. The defining feature is shared fate. Containers in the same pod are always scheduled onto the same node. They start and stop together, and if the pod is moved or destroyed, all of them go with it. That is precisely what you want for a helper that is meaningless without its main app. The rule of thumb is important though. Only group containers in one pod when they are genuinely a single functional unit with a helper relationship. Separate applications that merely talk to each other belong in separate pods. Use multi-container pods deliberately for true sidecars and AT2 not as a way to cram unrelated services together. So the takeaway, most pods hold one container, but a pod can bundle a few tightly coupled containers, and A2112, classically a main app plus a helper sidecar, like a log shipper and A2112, that share the same node and the same fate. Group containers this way only when they are truly one functional unit, not merely related services. What actually makes the containers in a pod a unit, rather than just containers that happen to be near each other, is what they share. And they share two important things. First, they share a network. A pod gets a single IP address, and all the containers inside it share that address. This means they can talk to each other simply over localhost, as if they were processes on the same machine, and A212. The main app and its sidecar communicate with no network hop, no service discovery, just localhost and a port. From the outside, the whole pod appears as one network endpoint with one IP, and the containers within divide up the pods. Second, they can share storage through volumes. A pod can define a volume and A212, a shared file system and A212, that its containers all mount, so they can read and write the same files. This is how a sidecar can process files the main app writes, or how two containers can hand data back and forth on disk. The volume belongs to the pod, so all its containers have a common place to share data directly. Together, shared networking and shared storage are what make co-location meaningful. This is exactly why tightly coupled containers go in the same pod. They can collaborate as intimately as processes on one machine and 800 to world talking over localhost, sharing files and 800 200 because within the pod, that is effectively what they are. And it underlines why unrelated services should not share a pod. You only want this intimate sharing between things that are genuinely one unit. The pod is not just a bag of containers. It is a shared context, an A212, one network, one storage space, an A212 that binds its containers into a single cooperating whole. So the takeaway? Containers in a pod share one network, an A212, a single IP. So they talk over localhost, an A212, and can share storage volumes to read and write the same files, which is what makes them truly co-located, and is the whole reason tightly coupled containers. And only those belong in the same pod. To work with pods effectively, you need to know how they live and 8-12-12, the phases a pod moves through from creation to completion. When you create a pod, it starts in the pending phase. This means Kubernetes has accepted the pod, but it is not running yet, an A212. It is being scheduled onto a node, and its container images are being pulled down. Pending is normal and brief usually, but if a pod is stuck in pending, that is a signal an A212, maybe no node has room, or an image cannot be pulled. The phase is already telling you something. Once the containers are pulled and started, the pod enters the running phase and it is halvol. It is up. Its containers are executing, and it is doing its job. This is the healthy, steady state you want your application pods to be in. For a long-running service like a web server, running is where it should sit essentially forever, serving traffic. Seeing running tells you the pod is alive and working. Finally, a pod can reach a terminal phase. If its work finished successfully, an A2012, which happens for pods that run a task, and exit an A2012, it enters succeeded. If something went wrong and a container exited with an error, it enters failed. Reading these phases is your first diagnostic tool. A quick look tells you whether a pod is waiting, working, done, or broken. When you inspect pods with kube control, this phase is one of the first things you check in A2112. It is the pod telling you, at a glance, exactly where in its life it stands. Learn to read the phase, and you can immediately orient yourself when something is wrong. So the takeaway, a pod moves through phases and A212, pending while it is scheduled and its images pull, running when its containers are up and working. And then the terminal succeeded if it finished cleanly or failed if a container errored an A212. And reading the phase is your fastest diagnostic of a pod in a tiny I state. Now, the single most important fact about pods and 8-212, the one that shapes the entire design of Kubernetes above them. Pods are ephemeral. Ephemeral means disposable, temporary, not built to last. A pod can die at any time, and A212, a node fails, the pod is evicted to make room, a container crashes, and A212, and here is the crucial part. When a pod dies, it stays dead. Nothing about the pod itself brings it back. There is no self-healing built into a lone pod. If that were the whole story, Kubernetes would be terribly fragile, with dead pods littering your cluster. It gets more pointed. Even when a pod is recreated to replace a dead one, it is a brand new pod with a new identity and, importantly, a new IP address. The replacement is not a resurrection of the old pod, it is a fresh one that happens to run the same thing. This means you can never rely on a specific pod being there, and you can never rely on a pod in 309 SIP address staying constant. Anything that hardcodes a particular pod or its IP is building on sand. Now, this sounds like a weakness, but it is actually the foundation of Kubernetes on TICE, resilience, and AT2 because it forces the right design. Since individual pods are disposable and their addresses change, you are pushed to treat pods as cattle, not pets, interchangeable, replaceable units you never grow attached to. And it explains the shape of everything above the pod. You need something to automatically replace dead pods and maintain the count you want, and you need a stable way to reach pods despite their changing IPs. Those needs are exactly what controllers and services provide. The ephemerality of the pod is not a bug, an 8202 how. It is the reason the rest of Kubernetes exists in the form it does. So the takeaway, pods are ephemeral and 8212 disposable, and when one dies, it stays dead. With any replacement being a brand new pod with a new IP and 812s, so you never depend on a single pod or its address. This very disposability is what forces the resilient design of controllers and services above the pod. That ephemeral nature leads directly to a practical rule about how you actually run workloads. So let us make it explicit. Because a bare pod does not heal itself, an 828282. It dies and simply stays dead, an 828282. You almost never create pods directly in real work. A lone pod is fragile. Lose the node it is on, and your application is just gone, with nothing to bring it back. Running naked pods is fine for a quick experiment or to learn, which is what we do in today in 2-9-man slab, but it is not how you run anything you care about keeping alive. Instead, you let a controller manage your pods for you. The most common is the deployment, which you glimpsed in the object model class. A deployment holds a desired state and 812 Tah1, 821. I want 3 replicas of this pod running 821, 821, and 821, and it continuously watches. If a pod dies, the deployment notices the gap between desired and actual and creates a replacement automatically, restoring your count. You declare how many pods you want, and the controller relentlessly makes reality match, healing failures without you lifting a finger. This is the object model from last class in living action. You do not manage individual, mortal pods, you declare a desired state, and a controller reconciles reality toward it, treating pods as the disposable units they are. So the mental model for running real applications is define your workload through a controller like a deployment and let it own the pods and A212, creating, replacing, and scaling them and A212 while you think in terms of the outcome you want. Pods are the atoms, controllers are what keep the right atoms in place. That is the pattern you will use for essentially everything you deploy. So the takeaway, because pods do not self-heal, you rarely run them bare, and A212. Instead, a controller like a deployment holds your desired count and automatically replaces failed pods to maintain it. So you declare the outcome you want and let the controller own the disposable pods, which is the object model in living action. Before we recap, let us connect this to what you will actually do at the keyboard, since this is a hands-on class. The core commands are ones you already met in kubectl class. Use getPods to list your pods and see their phase an 8021 to all pending, running, or a terminal state an 8021 and how many are ready all at a glance. This is your constant first check. Are my pods running as they should be? Now when something is off, getPods is where you start, because the phase and ready counts immediately point you toward the problem. When a pod is not behaving, describe the pod for the full story. Describe shows you the pod in TN9's details and, crucially, its recent events and 82 to fall, and those events usually explain a problem directly. An image that failed to pull, a node with no room, a container that keeps crashing. And to see what a container is actually doing or saying, read its logs. Between the phase, the events, and the logs, you can diagnose the large majority of pod issues quickly. In today in T39, lab you'll create pods directly and AT-OTUPL. Yes, the bare pods we just said you rarely use in production and AT-OTUPL, precisely because it is the clearest way to see the concepts up close. You will watch a pod go pending then running, exec into it, see its single IP, look at its phase and events, delete it, and watch that it does not come back on its own, proving its ephemerality with your own eyes. That hands-on experience makes every abstract point Today concrete. Learn the pod at this level directly, and when you move up to deployments and services, you will know exactly what they are managing underneath. So the takeaway? Inspect pods with the kube control commands you know and A212. Get pods for phase and readiness. Describe for details and the events that explain problems, and logs for what a container is doing, and A212, and today an A200 200 200 200. To see their life cycle, shared IP, and ephemerality firsthand. Let us gather the whole class in one breath. A pod is the smallest deployable unit in A212. Kubernetes manages pods, never bare containers. The container is your running app. The pod wraps it with the cluster identity, networking, and lifecycle. A pod usually holds one container, sometimes a main app plus a helper sidecar. Containers in a pod share one network, an A212, one IP over localhost, an A212, and can share storage volumes. A pod moves through phases, pending, running, then succeeded, or failed. And pods are ephemeral and disposable, so a controller keeps the right ones running for you. Next class, N8212. Deployments, running and scaling pods reliably. One idea at a time. That is the pod. Up